Today, we are primarily going to talk about the computing engine behind Hadoop. Okay, why the architecture and what's the need of it, and how does it work exactly? Okay, earlier we talked about why do we need big data, also known as distributed computing, and then we talked about a distributed file system called HDFS, where the files are sliced into small pieces and distributed on multiple computers. Then we talked about we talked about a problem of processing. Okay, so why when we talk about processing, why we talk about sorting in general? Processing could be anything. Okay, processing could involve as simple as multiplying 3 by 4. Okay, or processing could be as complex as doing certain very complex mathematical operation, like compression is a very complex mathematical operation. When you zip a file or uncompress a file, it's a complex operation. Okay, so why do we talk about sorting as the benchmark for computing? So there's a common scenario in the industry, in the computing industry. Whenever we talk about processing, meaning we are doing heavy processing, what we generally take an analogy of processing with sorting. Okay, why do we do that? So question here is, why do we take sorting as processing thing? All right, let's say select star from a table where name equals Sandeep and name has index on it. Okay, does this querying involve sorting in any way, or is impacted or related to sorting? Is creating an index on a table get impacted by sorting? Yes. So when we say select star from this and name has an index on it, suddenly if a column has index on it, meaning we prepared a kind of index on the backside of the book, suddenly the lookup becomes really fast. All right. As an example, if 100 records were taking 2 seconds. Okay, if 100 records were taking 2 seconds, 1000 records would take 3 seconds. And 10,000 records approximately would take 4 seconds. So that's the magic. That is the magic of the indexing. Okay? So if you had 100 books to search in, if it's taking 2 seconds for you, okay, in the index, if you had 1000 books, it will hardly take 3 seconds. All right, so that is the power of the indexing. All right, next question is, when we say select star from a table, order by name, does it involve or get improved by indexing on name? Yes, ordering is of course sorting. So select star from, so order by is of course impacted by sorting algorithm. Now let's take a third case. Select star from table, group by name. Now does it involve or get impacted by sorting? If you have to do group by, what is it that you will do? Let's say I give you a list of names and I want you to create groups of the same name. Okay, so what will you do? What will be the easiest way to do the group by? All right, so the easiest way of doing the group by is using the sorting. Okay, so group by is essentially equivalent of sorting. All right, next is say select star from table 1, comma, table 2. Here we are joining two tables, table 1 and table 2. So when we join two tables, okay, the great way of joining is that you sort both the tables, okay, like this, okay. So you join the two tables, table 1 and table 2, by the way of ordering the two tables by the column on which we are joining the two tables. Okay, so here we are joining table 1.x and table 2.y. What does it mean? How would you actually, if I give you physically, if I ask you that, hey, these are the two lists, can you please bring the user's name and their age together? One table containing name and other table containing the age. Okay, and you have to join based on certain ID. So how would you do it? What will be the easiest way to do it? The easiest way of doing it is you sort both the tables by the column on which it's being joined, and then you put them side by side, and then bring them together, bring the records together. So if you sort them, put them side by side, suddenly the whole performance, after sorting, the whole performance will be really, really great. Okay, so this is a very easy way of joining the two tables. So what is it that I've tried to prove just now? Almost every command related to SQL, almost every command that is generally involved in data churning involves sorting under the hood in one form or another. So most of the in our normal data world, most of the problems could be converted into a sorting problem, into, at least they are converted partially into sorting problems. Okay, as when we go forward, you will see that the very complex problems itself we will be able to break down into sorting problems. If we can break down into a sorting problem, the problems becomes solvable. If we can't break down a very complex problem, as in a problem that requires many iterations, if we can't break it down into a sorting problem, then we generally can't solve it. Okay, so therefore a sorting problem is a very important one to solve, and you will be amazed at how many algorithms exist for sorting problem for exactly the same reason. So all I've tried to explain is that most of these technologically challenging problems involve sorting in one form or another. And therefore, that is the reason why Hadoop is basically a big mammoth sorting engine. It sorts data using so many computers. All right, that's what is MapReduce. We'll go into the details bit by bit. All I want to do is bring your focus to the sorting algorithms right now. Okay, so all right, so we will discuss MapReduce. All right, but before that, let's try to understand how to get the work done using many computers. Okay, in Hadoop you get the work done using many computers. All right, so the lower bottom part here, this one we have already discussed, right? There is admin node or name node, then there are data nodes, they're storing data. Now, interestingly, in Hadoop, since these computers which are serving the data, which are data nodes, are comparatively free processor wise. So on all of these nodes, we install a process called task tracker. And on one of the nodes, we generally dedicate as job tracker. So job tracker and name node, although they are installed on the same machine in this diagram, but in real life, they are generally on different machines. All right. So I take a step back. So to get the work done by using many computers, Hadoop uses something called MapReduce engine. This is the version 1.0. I want to first talk about version 1.0 and then we will talk about 2.0. Okay, the reason why I'm talking the older version first, because it makes the life easier. It makes easier to understand. In MapReduce 1.0, MapReduce did the computing in the following manner. First, in Hadoop, what they did was they made sure that the work could be divided into multiple machines. Okay, so what they did was they created master and slave kind of architecture, just like Hadoop, HDFS. In HDFS, you have one master and rest are just storing data. Here, there is one master and we call him job tracker. Job tracker basically does nothing but interfaces the customer. So if you want to get something done from the job tracker, you will ask job tracker to do things and job tracker will assign the work to the task tracker and task trackers will finish their work, and once they are done, they will store their output in HDFS. Alright? Whenever we give the work to job tracker, it gives the work to task tracker. Okay. Now question is, does every processing get done on all the nodes? No. Only the nodes which are near to the data. Okay. The other way to look at the model is there is a client. Client goes to job tracker, hands over the work, and job tracker gives the work to task tracker. Okay. All right. So job tracker gives work to only those task trackers which are nearer to the data. Okay, so these are the data processing works. Most of the works are basically related to processing certain data lying in HDFS. Okay, although there are some works which do not require any data processing, those kind of work get done on the choice of the job tracker. Okay, so there are many considerations which job tracker does while assigning the work. First, which one is closer to the data? As we already discussed in the previous sessions, that data gets stored on the data nodes, right? Data gets stored on the data nodes. Every machine is having some part of the data. And when we run a logic, what happens is the logic goes to only those task trackers which are running very close to the data. So there might be multiple data nodes, but only those will be utilized which are closer to the data. Second consideration while assigning work is which data node is more busy. If data node 1 is busier than the data node 2, since job tracker is keeping track of the jobs, okay, next job will not be given to the job tracker, instead some other node nearer to the data. And in case one task tracker does not respond, job tracker assigns work to somebody else, and that somebody else will start working again. And in the same way, if some other task tracker fails, the work will get delegated to somebody else, and that's how the whole job tracker task tracker philosophy works. Okay, so now let's talk about the job tracker. All right, this is a very quick overview. We will go into exact semantics again. So a user submits this. This used to be the old MapReduce way. Okay, so the user submits the job after he has copied the data to the file system. So again, most of the MapReduce computing was about churning the data which is already stored on the cluster. Okay, so the first step for the user was to upload the data on the file system, and then second step was to submit the job referring to those files. And then this client means client driver, the command called Hadoop, okay, will find out the information about the files, will then submit the job to the job tracker. Okay, and then the job tracker will create maps and reduces, put them into job queue, and then get the work done over the cluster. This map reduce you can ignore for time being. I will take a detailed consideration into this. So the client driver called Hadoop will assign the work to job tracker. Job tracker will further assign the work to the task tracker by the way of defining queues. There are multiple queues for tasks, and and for each queue it creates, for each task it creates kind of slots. If you have gone to restaurant and you place an order to the waiter will take your order and put it into a slot, while once the cook has prepared the food, it will bring the food and put it near to the slot, which waiter will bring from the slot to you. Okay, in the same manner it creates something like some data structure in which every task status is marked, whether task is working or not, whether basically it's the status of the task that is maintained by job tracker. In case any of the things fail, job tracker will assign the same work to somebody else, and heartbeats are sent to all the task trackers continuously to monitor whether they are up or they're down. All right, again, so client asks job tracker to get the work done. Job tracker further delegates to task tracker, and client can ask that he needs 20 task trackers or 5 task trackers, and client, that is optional. By default, the number of task trackers dedicated to a job will be decided based on the file. All right. Earlier, what used to happen was the logic as well as this. So just now, whatever we saw was that there's something called MapReduce. There's something logical, as in the way of doing the operation, like the way when we execute some logic on SQL server, we give SQL query, right? When we execute the logic on SQL server, we give SQL query, right? So, and that query gets executed in whatever manner. In the similar way, when we used to talk to MapReduce, we will structure our logic into map and reduce. Okay, so we would structure our logic into map and reduce and we'll give it to the job tracker. So earlier in Hadoop 1.0, there was only one kind of logic allowed called map and reduce. Okay, and everything was being done by this framework called MapReduce. The same framework was doing the job tracker, task tracker, as well as at the same time it was doing the MapReduce. So everything was only in one form. So you could not do computing of any other form than MapReduce. It's like saying database saying, hey, we only allowed SQL. We don't allow any other kind of system. Although the things like job tracker, task tracker were of very much use for many more systems. Okay, many more systems. Because what does job tracker, task tracker do for you? Job tracker, task tracker make it happen that get anything done through us. It does not enforce. Job tracker, task tracker is a flexible architecture. It can accommodate all kinds of computing requirements. Okay, therefore this MapReduce was very limiting because it was a single system containing both, and this job tracker, task tracker was being only used by MapReduce kind of jobs. Okay, therefore it was monolith, meaning a single system which is non-separable. Okay, and that's where people from Yahoo decided to break it down into two parts. One was called pure MapReduce. Okay, one was called pure MapReduce and other was called yarn. Okay, it's earlier it was as if the somebody has bundled operating system with the database. Old MapReduce was as if somebody has bundled MapReduce database along with the operating system, and this system says that, hey, I can't do anything else other than MapReduce. So that was MapReduce 1.0, and that got broken down into two parts. One was called MapReduce, pure MapReduce, just the data processing using MapReduce. Other was called Yarn. Now this refactoring, this is basically refactoring. Refactoring means breaking a larger piece into two smaller pieces. Okay, this refactoring allowed lot of innovation to happen. Now you are not happy with MapReduce, you come up with something else. Okay, somebody needed a kind of Spark, and they wrote Spark. Then many more innovation came in the form of MapReduce, similar to MapReduce. Now you can see that as soon as that happened, as soon as this resource management, like which task tracker is free, which one is busy, tracking all of that was taken out and put something into Yarn. Now Yarn contained only the logic that involves assignment to task tracker, assignment to job tracker, and so on. So it's like we have taken the operating system out and made it available such that this operating system can execute everybody's programs, not only of a particular party. Now this opened the door for a lot of innovation, such as the MapReduce was anyway there. These is an alternate to MapReduce internals. Then HBase. HBase amazingly runs on Yarn. Similarly, it opened the door for Storm, Giraffe, and Spark. Is continuously competing and changing the way people did MapReduce. Okay, people are moving to Spark as of today. We will cover full 3 hour session of Spark, a proper hands-on version. Okay, and so there are many more systems that came because of breaking the MapReduce and separating out MapReduce from Yarn. Okay, so what does Yarn do? Yarn provides you a way of executing your logic on many machines. Any program you give to Yarn, Yarn will launch it on many machines. Okay, and from the you will assign the work to Yarn, and that's it. All right. So again, Yarn supports workloads other than MapReduce. It provides you the scalability. An interesting part was that whatever older programs of MapReduce were there, they were comfortably running on top of Yarn. Okay, let me recap a little bit. So when we talked to MapReduce, so MapReduce contained everything. First, it contained all that task tracker, job tracker kind of model, where job tracker was doing tracking the task trackers and getting the work done through task trackers. Plus, when we assign work to job tracker, we were only able to assign the work in the form of MapReduces. We provide two pieces of logic. We used to provide in MapReduce 1.0, we could only provide two pieces of logic. One was called mapper, other was called reducer. And that logic was run by job tracker and task trackers such that you get the results. Okay, mappers were run on all the nodes, and once the result was produced by mappers, it was gathered together, and then reducer was run on the aggregation. Now interesting part was that you could only program on Hadoop cluster using MapReduce earlier, and that's what was broken by Yarn. In Hadoop 2.0, the same MapReduce became Yarn plus MapReduce. Okay, the common part, the common resource management part. See, as you just saw that you have so many questions related to resource manager. Can it handle this? Can it handle this? Can we say that use 10 task trackers? Does it track which one is busy, which one is not? Does it track which one is closer to data, and so on? So from the discussion itself, purpose of a resource management is is very high. The need of a resource management is really high, and that's where the need of yarn was there for all of the other people. Okay, so it made it possible. This Hadoop, had Hadoop 2.x was not in place today, the need for Hadoop would have been very limiting. Okay, so whatever we called job tracker in MapReduce 1 became multiple things in yarn. One is called resource manager, other is called application master. So job tracker became resource manager, application master, and timeline server. And task tracker became node manager, and slot became container. Slot as in individual tasks slot. Okay, now here is a little complex diagram. All right, it's as if there is a country. Okay, I'll try to draw this. I think that will do a big magic. Okay, so let's just take an analogy. Okay, so I'm trying to explain how does yarn work. Earlier we discussed how does MapReduce work. There are mapper, there are task trackers. Okay, so there are, in case of MapReduce 1.0, in the older system, there was job tracker and task tracker. In here, we have different things. We have resource manager, and then there are multiple nodes. So on each node, we have node managers. And whenever client comes along and says, hey, I want to get something done, so client has also have to tell us that what is that something they want to get done. He says that, okay, my work is related to this new framework and I know how to get my work done. So resource manager says that can you give us kind of a logic? How would you run your system? Okay, so client will also give the complete logic to the resource manager, and that logic would be run in something called application master. There is an application master for every kind of consumer of yarn. For example, there is an application master for MapReduce, there is an application master for Spark, and so on. So application master is kind of the representative of the framework which we are using. Client want to use some new fresh framework which is not there on yarn, they can submit their framework along with that, and that framework will be run as application master. Okay, it's a kind of a government. It's a kind of a government that government says there is a PM office. Okay, I'll just try to simplify a little bit, and then there are states. Okay, these are, let's say, two states. Okay, let's say some two state 1 and state 2. Okay, now Microsoft comes along and says to PM that, hey, you know what? I want my Windows to be built in your country. Can you devote us some location and resources? PM says, okay, I don't know how to build your Windows, but I know that there are people in these two states. Why don't you go and establish your office? So Microsoft goes and says that here is my headquarter. Okay, this is kind of Microsoft headquarters. Okay, and that's kind of application master. Okay, I'm trying to take an analogy. All right, now this is a headquarter. Okay, and then there are people working at various places. Some people here. Okay, some work is being done in KA, and some work is getting done in AP. Okay, the Microsoft headquarters know how to get their work done. Okay, there are workers here and here. That's what is happening. So the client, which is Microsoft, came to PM and said that this is what we need close to 1,000 people, and we need close to highly educated people and one office. Okay, so this is what happens. All right. In the similar fashion, some other company, say Amazon, comes along. Okay, some Amazon or say GE comes along, and GE says that hey, we need 5 headquarters. Also, in case of Yarn, there is always one headquarter. So let's settle it down. Okay, so instead of earlier in Hadoop 1.0, this guy, the job tracker, was trying to get everything done. In new case, the client also submits the application master. Okay, so Microsoft came, talked to PM and said, I have my people who are supervisors and the directors and everything. Okay, they will be my application master. I'll get my work done. Just give me a place to stand and the resources. Okay, so this is an analogy to what's going on here. So the client comes and says, hey, I want to get my MapReduce work done. Okay, so resource manager talks to these node managers, and here node manager means the chief minister of the CM of each state. Okay, CM of each state. I thought about this analogy. This analogy is actually fitting very much. So this resource manager talks to each individual node manager and says, hey, we need 5,000 people. Do you have 5,000 people? And then node manager says, yes, we have 5,000 people. And resource manager also says that we need one dedicated office for the headquarters, and that becomes the application master. So every client, okay, in case some other Microsoft users come in from outside, they will also be redirected to same application master. So every framework comes with the application master, okay, along with the need what they want to get done. All right, so this is how it works. Let me just describe once more. Okay, so here it is. The node manager is per node agent. It's like chief minister of the state. These are states: state 1, state 2, state 3. This is the country chief. Okay, so the node manager here is per node agent. It manages and enforces resource location allocations. Okay, then there is application master. Application master are per application. Today it's Microsoft which came in that my work needs to be done. Then after some time the Wipro came in that hey, my work needs to be done, and so on. So this application master is only one. There is only one headquarters, okay, who manage their container, as in their zonal offices. All right. So application master manages the application lifecycle and also takes care of all kinds of work scheduling. In case so, if we are running a MapReduce task, application master will be deciding how many maps, how many reduces, and so on. All right. So the way it happens is the client submits their application. Client not only submits a small query or the logic, it also submits the full application. And this application brings the logic that needs to be done inside application master. So client submits the app, resource manager launches the application master inside the container. Okay, and so the client submitted the resource manager consulted with all the node managers, and whichever node manager can run application master and is most free, that machine, that node manager, that node will be given the application master. Okay, so it's like setting up the headquarter in the state where the taxes are lowest and there is a lot of land available. Okay, and container is a form of office. Okay, so no matter what you do, the work always gets done inside container. Application master is also running inside container, so everything gets done inside container. So resource manager launches application master inside a container, and then application master registers with the resource manager so that the users of this application master can contact it. Okay, all the users of Microsoft can contact this headquarters. Okay, all the people who are coming from US or somewhere, or who are going to the US, they can talk to the headquarter directly. They don't need to establish the headquarters again. Okay, so the application master asks for the containers, and they get it. So again, once you establish the headquarters, they will again raise a request that, hey, we need 20 containers, as in 20 more smaller offices in the country. Okay, give us those. And then those containers would be availed by various node managers, and once that is done, the the application in the container talks back to the application master. So any work that is getting done for this application master will get done inside various containers. Okay, and these containers will talk back to application master, and then and then client can talk to the resource manager and talk to the application master and take the status as what's going on. Okay, and once everything is completed, application master deregisters itself from the resource manager and get out. Okay, and shut down. All right, so that was a way of understanding yarn. All right, so you can look at the other way as well. So application client submits the work to the resource manager. Okay, we are submitting the yarn application. All right, and the resource manager, the prime minister, the resource manager is assigning the work to the node manager, and node manager is creating a container for the application master. An application master registers back to the resource manager, hey, I'm up, and then starts working on actual work, start focusing on the actual work at this point. And what does it mean by actual work? Actual work means node manager and the containers. I mean, more containers will be created for each application master, and that's how it goes on. All right. So a resource request. When a client is making a request to the resource manager, it creates something called request. It's called resource request. And resource request could include how many containers do you want, how many memory of each container, and how many processors do you want. Okay. Along with that, do you have any locality constraint? Meaning, do you want to enforce that your containers should be only on the node where the blocks of a particular files are available? That is locality constraint. So when you are making a request, you could tell, hey, my work is very heavy, I would need so many containers, and I would need so much memory on each container, and I would need these many total CPUs. Along with that, you could tell Jan that, hey, my request to you is, please run my logic near to this particular data. That is locality constraint. You could make the request of all these resources upfront, as in you could make this request to resource manager directly, the client could make it directly, or let my establishment start, and then the further requests could be made by application master. Further requests could be made by the application master. Okay, So that is, either you could ask for upfront while from the resource manager, or you as in the client might ask the resource manager, or the application master would ask for number of containers. Okay, now the application's lifespan could vary too dramatically. It varies too much. There are some applications which keep running forever, and then there are some applications which run only for few seconds. Okay, so generally the lifespan of a process is of three parts. Okay, just one application per user. Other is one application per workflow, meaning you started a session, keep on working, and then the third one is long running. All right. So if you want to build your own yarn application, first try to use existing frameworks such as MapReduce, Spark, etc. Second, try to use existing tools to build jobs such as Apache Slider and Apache Twill. And otherwise, if you want to build, be aware that building from scratch is complex. Use Yarn projects bundle called distributed application if you want to build your own. Okay, all right. So you could do a cluster hands-on. For quickly, I'm running the MapReduce example here like this. Okay, okay. So it says that it's not a valid jar. Don't worry. So we will just find it out. What's the valid jar then? I'll just put current. That's better way to keep. What? All right. Let me just find out. Let me just find out. Let me just find out the example. All right. So here we go. Can't we just put? Okay. So where is my command? All right, so I'm trying to execute quickly this MapReduce command. Right now, just for give you a taste of it, I want to show you how does a MapReduce command looks to you. All right, so here we go. So here we are saying Hadoop. Earlier we said Hadoop FS. Okay, where is that? We said Hadoop FS. This time we are saying Hadoop jar. Okay, so we are telling Yarn that hey, my logic is in this program and we are trying to execute MapReduce. Okay, my logic is in this program and my input folder is here and output folder is this one, and since the output folder already exists, it gave us the error. So let's just say 6deb. All right, so you can see that it has started a background process which is running for us. This is called batch process, and you can see the URL. It says they cannot assign the requested address probably. All right, so looks like now the request has been assigned. I don't know which machine is that. If it's not A, let's try B. B is not there, let's try C. Okay, C is there. Okay, so it says that there are total number of one map, one reduce, and something is happening. And it has finished executing. And it has saved our output in mrout. Okay, I'll show you. Where is my home folder? All right, so, all right, you can see mrout. This is what it just created. And This file represents the process as finished, and this is the output file. Had there been many phases, then there could have been more data. So we just computed the word count using the example internally provided. Okay, so all we did was we basically run the this command. First we found where are the examples located. Okay, so you could also run it. All right,